Howdy, y'all. Here we're given a representation of some motion on a position time graph, okay? The representation here, let's say, is somebody walking in the agra. They start 10 meters away from the origin. Perhaps the origin is the door, so they're 10 meters away from the door, and they're walking away from the door, right, for 10 seconds, until after 10 seconds they get to be 30 meters away from the door. What we have to do is we have to represent that same motion as an equation, as a motion map with words, and as a velocity time graph. We're going to put the equation up here. Here's our space for the motion map. Here's our space for the velocity time graph, and we'll put some words down here in this bottom right space. Okay, let's start with the equation. First thing I notice that this shape is a line, and when we see a line, one way to write the equation for a line is in the form y is equal to mx plus b. Now, in physics class, these variables y and x mean something specific, and in this case, y means position. So I'm going to write position is equal to, we haven't yet found the value of the slope, so we don't know what m and b, or the value of the y-intercept. So I'm going to leave those as n. But we do know what the variable x means, right? X in this case is the time, okay? So I'm going to write n times time plus some value of b, okay? Now let's find those values. Well, b is the y-intercept, is the vertical intercept. That one might be easy to see on the vertical axis here, on the position axis. At time 0, we start at position 10. So b is a value of 10 meters. It needs to mean something. The meters tells us what it means. M is going to require a little calculation. Let's do rise over run to calculate the value of m. So here we have how much the line rises over how much the line runs. And we see that it rises from 10 to 30 meters. So we do 30 meters minus 10 meters to get the rise of 20 meters. In how much time it runs from 0 seconds to 10 seconds. That's a total of 10 seconds. Now if we do rise over run, that's 20 meters over 10 seconds. Which of course, 20 divided by 10 is 2. We got to keep those units meters per second. And what that tells us is that tells us the velocity of this object, of the person walking in the agra. The person is walking 2 meters per second. Okay, so let's finish our equation then. Instead of m here, we can just write 2 meters per second. And I got to keep the units because the 2 needs to mean something. Okay, we're going to say that equals the position, and the position is, you can write out position, that's just fine, or you can represent it with the variable x, with the letter x. Okay, so we have x is equal to 2, that's the slope, times time, and again I'm just going to represent that with t, plus our y-intercept. In this case, our y-intercept is 10 meters, so plus 10 meters. There we have represented the motion on that position time graph with an equation. So we're done with the first part. Hooray! All right, now we have to do a motion map, okay? And to start with, I just put my first dot where the object starts. And we know already that the object starts at position 10. So I'm going to put my first dot there. After doing the equation, we know that the object goes 2 meters every second. And we also know from looking at the position time graph that that goes 2 meters away from the origin. So it's going to positive 2 meters per second. That means the next second, it's gone 2 meters away from 10, position 10. It's gone to position 12 meters. Okay? I'm going to draw an arrow between those dots showing that it moved there. Then second after that, so at time 2, it's gone another 2 meters. It's gone from position 12 to position 14. Okay, again, I'm going to draw an arrow between there showing that it moved. Now, every second, it goes another 2 meters. Okay? So I'll draw some more dots with those arrows, and then we're going to go back and count. So we have time 0, time 1, time 2, time 3, time 4, time 5. This shows us that at time 5, the object is at position 20. Let's double check that. If this is our time axis, we have time 5 in the middle. And it looks like right about there, at time 5, the position is 20. So in this case, our position time graph matches our motion map. Let's continue to go every second the object goes 2 meters. And then I'll draw the velocity vectors, the velocity arrows. Now if we have time 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, we see that at time 10 it's at position 30, and again that's what our position time graph tells us. Time 10, we're at position 30. So once again, our motion map matches our position time graph. Our motion map also matches our equation. Every second it goes 2 meters, and it starts at position 10 meters. Now let's make a velocity time graph. The velocity time graph is unique from the position time graph. What is happening to the velocity? Is the velocity changing, or is the velocity staying constant? And we know that the object every second goes 2 meters. So to answer that, the velocity is staying constant. On our velocity time graph, we need to show that the velocity stays constant. The velocity does not change. And the velocity is always 2 meters per second. So you might notice that I don't have the axes labeled here. I'll start with 0. It just needs to go up to 2. So I'll just say that's 1, and that's 2. Okay? And then we just need to show that the velocity is always 2 meters per second. Okay? So for all 10 seconds, the velocity is 2 meters per second. I should have units on my axes here, and the units for time in this case are seconds. All right, finally, the last thing that we need to do is just write what is happening in words. Okay, so the object, the person, whatever it is, the object starts 10 meters away from the origin, which in this case might be the door in the agora. The object moves a positive 2 meters each second, or the object moves with a velocity of 2 meters per second for a total of 10 seconds, right? You could say something like, until it ends 30 meters away from the origin, or for 30 seconds. In this case, we have our position time graph represented as an equation, as a motion map, as a velocity time graph, and as words. Nicely done.